So this is the first video for Unit 15, which is trig solving. And the first example that I want to look at is sine of x is equal to 1/2. So in the previous units, in order to solve this, we think about what angles will make this statement true. So sine of 1/2 is going to be up vertical by 1/2 because sine is y. And the two angles that we get are pi over 6 in quadrant 1 and 5 pi over 6 in quadrant 3. So we always, well, so far we've always used just the original unit circle. So just from 0 to 2 pi. Now, if we take a look at this next one, it is sine of 2x is equal to 1/2. And if we wanted to find the possible solutions from, let's say, 0 to 2 pi, because that's the one revolution of our unit circle that we've been using, we'd have to approach this a little bit different because of that 2. Now, we might look at this and be like, oh, we can expand it. Let's do 2 cosine x sine x. This is not a good idea because now you have multiple trig equal to a single constant, and we want to avoid that. So there's actually going to be another unit that you do for this one, and that's going to be using inverse trig. Because what I want to do is try and undo the sign so I can isolate the x from here. So it's actually not a bad thing that we have sine 2x right now. So I'm going to rewrite this as arcsine of sine of 2x is equal to arcsine of 1/2. And what this will do is it will undo the arcsine and the sine, and then we're left with 2x over here. Now, arcsine of 1/2, that's essentially what we do here. It's a mid-step that we don't usually write, but the arcsine of 1/2 will be pi over 6. Now, people are going to start thinking, but what about, shouldn't that be negative pi over 6 because arcsine is in quadrants 1 and 4? That is true if we were only talking about arcsine. But because we are talking about sine, this has a unrestricted domain, all right? So we have an infinite number of solutions for these. So yes, we are using arcsine, but we are using it as a means to an end for sine, which has a solution in quadrant 1 and a solution in quadrant 2, okay? So now this will be, we will have pi over 6 and 5 pi over 6. And I'm going to write it as a set like this. So I have pi over 6, 5 pi over 6. Now, this is the same as writing 2x is equal to pi over 6 and 2x is equal to 5 pi over 6. This saves a lot of time and it saves a lot of space as well. So you don't have to use this. You could list them separately if you want to, but in my examples, I will be writing it like this to save space and time. Okay, so the next part in isolating x is a lot of, in the past, we would say, oh, divide by 2, divide by 2. But now we're looking at pi over 6 divided by 2, which you should know how to do. But again, we want to talk about efficiency and saving time. My suggestion would be to use multiplication. We're usually more comfortable with this because we learn it before division. And it's easier to see what you will be multiplying with the denominator itself. So I'm going to multiply with 1/2. That way I follow the same procedure I did up here. I'm undoing the sign. So I'm also going to undo the 2 by multiplying everything by 1/2. So that isolates the x. And within my set, I'm going to have 1/2 times pi over 6. So that'll be pi over 12. And then I'll have 1/2 times 5 pi over 6, which is 5 pi over 12. Whoops. Now, if we're talking about the unit circle, this poses an issue, okay? Because sine itself, if I want to think about one period, is going to look like this. But sine 2x, that's a horizontal compression with a scale factor of 2. So now we don't only have just this one period within 2 pi. We have this. Let me see if I can draw it better. So we hit here and here. So now we have twice as many curves. And if I'm solving for 1/2, previously I had pi over 6 and 5 pi over 6. But now if I solve 1/2 with this new one, I have 4 solutions. Okay, 4 total solutions. And the first two are pi over 12 and then 5 pi over 12. But how do we get the other two? Okay, And that's what we're going to talk about in the next couple videos is how do we find those other two solutions? We have to go beyond just using 0 to 2 pi, okay? We're going to have to start exploring infinite number of options and then choosing the options that fit within our particular domain restriction. So in this video, or not in this video, in this unit, you need to remember your transformations because that can help shed a light on, okay, how many solutions will I have for this one? Or solution sets, I should say. Because I see that 2, it is a horizontal compression with a scale factor of 2, so I'm going to have twice as many solutions. So that's where I have my 4 solutions. You also need to remember how to use inverse trig because we're going to be going back and forth between coordinates and angles. You also need to know your identities. They will come in handy. And something else is algebraic manipulation. This is going to be very important, like what you did in Algebra 2 with factoring and solving and isolating and undoing things and redoing things. This is going to help you solve problems a lot quicker and more efficient. Now, what is a general solution or infinite solutions? Well, if you recall, the unit circle is not bound to just 0 to 2 pi. We use it a lot in order to get our angles and coordinates, but there are an infinite number of solutions. There's an infinite number of coterminal angles for every solution on the unit circle. And to find those, like for sine, because sine has a period of 2 pi, I can just add 2 pi. And then I can add it again, and then add it again, and add it again, and I will continue to land on that same angle or coordinate. Now, this would be I can write this an infinite number of times. It's not going to be efficient that way. So what do? We collect all of this, and we write it as plus 2 pi k. So if I want just to add 2 pi, k is equal to 1. Oh, but I want to add another 2 pi, k is equal to 2 then. But what about 3? All right, k is equal to 3. So this combines all of our infinite solutions into one solution set so that we're not trying to write them out every single time, okay? So if we go back to sine x is equal to 1/2, we have our original culprits. I have my pi over 6 and 5 pi over 6. So if I have pi over 6 and I want a coterminal angle as many times as I want, plus 2 pi k. And then same thing for 5 pi over 6. I'm going to add 2 pi k. They occur every 2 pi. K can be positive, it can be negative, it could be 0, as long as it's an integer. Now, again, we can write these as one set. So x is equal to, I have pi over 6, and then I also have 5 pi over 6. And for both of them, I add 2 pi k from their original location. So I can write plus 2 pi k. So the 2 pi k applies to the pi over 6, and it applies to the 5 pi over 6 independently, okay? So this is how I will be writing these problems out. You can do this, that's fine. It does take more time, so you might have to pause the videos to keep up, but it's up to you, whatever works best for you. You do need to recognize both though, okay? So even if you don't use one, you have to recognize the other. So for sine of x, we already talked about it. If we want our general form or infinite solutions, general solutions, we can write it out like this. For cosine, that's going to be quadrant 1 and quadrant 4 for cosine positive 1/2. So we'll end up with x is equal to, this is family of 3's. So I have pi over 3, 5 pi over 3, and cosine has a period of 2 pi, so these solutions will occur every 2 pi k. And then remember, k is an integer, but you don't have to write that. And then tangent. So we have tangent of 1. Tangent is equal to positive 1 in quadrants 1 and quadrant 3. Now, the period for tangent is pi. So if I start at pi over 4, I add a pi, I end up at 5 pi over 4. If I'm at 5 pi over 4, I add a pi, I end up at the coterminal angle for pi over 4. So this means I don't need two different solution sets. I can start with pi over 4, and then I can just keep adding pi, and I can nail both of those solution sets just with 1. And that's because tangent has a period of pi. And then just a quick reminder, we can write squared, cubed, quartic, any of them, but that power, it could be on the outside, or it can be right after the trig expression, but they both mean the same thing. Now, if you see this, sine of x squared, and the squared is inside of the parentheses, then that means that the argument is squared, not the trig expression. So understanding parentheses will be very important for this unit. So just look out for those. Alrighty, next video will be on finding general solutions without a calculator.